All right, Hassler here. I'm going to be going through the 11.3 notes on vertical stretches and compressions of parabolas. And so as we've been talking, parabolas are these U-shaped graphs produced by quadratic functions. And so let's take a look at problem one. Problem one says trace each graph in a different color and circle the matching function in the same color. Use the graph to complete each part. Well, my graph is already done in different colors. And the reason why I want to have you guys do the three different colors and highlight the function that goes with it is so that we're all on the same page as far as which function goes with which graph. As you can see, these graphs are really close together. And when we created this picture, we did our best to try to make sure that the function, the y equals function, matches up with the appropriate graph. And so let me show you this outermost function, which I have in green. Let's see if it'll let me do here. There we go. Which I have in green. So I'm just going to go over this with green. That's actually going to go with our parent function of y equals x squared. So I'm going to circle, I'm going to highlight the outermost function in green, and I'm going to circle that in green. My next function is in blue. So I'm just going to trace over that with blue. You can do whatever color you want. Okay, and that goes with the y equals 2x squared. And this last function I have here is in red. Again, whatever color you'd like. And I'm going to trace that out. But the big idea here is that we want to make sure that we know which of these parabolas goes with which function. And so if I trace my parabola in a given color and I circle the function that goes with that color, hopefully I can keep track of the equation that goes with the graph. Okay, so now let's go ahead and start answering some questions. It says, what function is the parent function? And so we had started talking in the previous lesson about the parent function, and the parent function is the most basic functions for quadratics, and a function has two parts, an input and an output. And so I need a y equals x squared. That's the most basic quadratic function I can have. All right, and that goes with that green graph down there. It says, what do the other two graphs, or how, do the other two graphs compare to the graph of the parent function? Okay, well, remember the parent function is green, so maybe we should just label that. I'm going to label that PF. That's my parent function, okay? And the other two functions looks like they're more narrow, right? More narrow than the parent function. Right, it looks like on the parent functions, let's talk about some points that are on these graphs. So on my parent function, I have the point 1, 1, and that's this point right here. But when I look at my other two functions, y equals 2x squared, instead of 1, 1, when x is 1, I have an output of 2, so 1, 2. And for y equals 4x squared, again, when x is 1, it looks like I have a point at 1, 4. All right. Kind of looks like, as I focus in on this x value of 1, it looks like my output is getting bigger as my coefficient of x squared is getting bigger. Okay, so larger output when a gets larger. I do notice that all have this vertex at 0, 0, right? And so we can get that in there too. All of them have this vertex of 0, 0. So there was no shift up or down in any of these graphs. How do the other two functions, okay, now we're looking at the functions. So how do the other two functions compared to the parent function? Well, here's the parent function, and the parent function really has a 1 in front of that x squared, versus these other two functions have larger values than 1, okay? So the a values are bigger than 1, and it looks like the larger the a value, the more narrow the graph. Okay, and that is true. That's always going to be true. And so I have an in general here. In general, okay, things that are always going to be true. When given a y equals ax squared, and when that a value is bigger than 1. These are both big ideas. These are big deals. And so I'm going to highlight when given ax squared where a is bigger than 1. Okay, then the parabola, remember the graph of the quadratic, has a vertical stretch. Okay, vertical stretch is one of our keywords then. Okay, so this vertical stretch. And when we talk about this vertical stretch, what's really happening is that we are being pulled upwards and away from the x-axis. I'm just going to make note of this. What this really means is that my graph is being pulled upwards, away from x-axis. Okay, and we see that here when we look at these ordered pairs. For the parent function, we are typically at 1, 1. But when I have this a value is going to stretch my graph so that instead of 1, 1, I'm at 1, 2. And when my a value is 4, I'm going to stretch my graph away from that x-axis, right? When x is equal to 1, these outputs keep getting further and further away from the x-axis. I'm stretching my arms way up to touch the sky. Okay, so pulled upwards, stretching my arms up to touch the sky. And that occurs when the a value is bigger than 1. Okay, we get this stretch. So let's see what happens here in problem 2. Again, we're going to trace each graph in a different color. So let's get our 3 colors back out. All right. So this time my outer function here is my red function. I'm going to trace that in red. And the function that goes with is the y equals 1/4 x squared. Okay. My middle function, again, is in blue. And the function that goes with that is y equals 1/2 x squared. And this last one is my parent function. I've got the equation y equals x squared, okay? So again, we're just tracing our graphs and then circling the matching equation in the same color. And again, A says, what is the parent function? Well, it's that y equals x squared, the most basic of functions where technically that a value is 1, okay? How do the other 2 graphs compare to the graph of the parent function? So this is very similar to the questions that we discussed up at the top. And to me, compared to that green parent function, these other 2 functions look wider than the parent function. So let's see what we wrote up above. We wrote, oops. And where did that come from? Oh, it came from right here. We wrote that they're more narrow. Okay, and so here we're going to write that these graphs are wider than that parent function y equals x squared. Okay. Again, we had picked out some points on that parent function. And so on that parent function y equals x squared, we have the point 1, 1. Okay. In fact, we had talked in class that that 0.11 is always on the parent function. But when I look at the next function, y equals 1/2 x squared, and again, I focus on this x value of 1, now I'm at the ordered pair 1 comma half. And when I look at the other function, y equals 1/4 x squared, and again, I focus on that x value of 1, I have 1 comma a quarter. And so what I notice is that my outputs are actually getting smaller. And they're related to that a value. I also notice that all of these have a vertex of 0, 0. Okay, and I know they have a vertex of 0, 0. They're all centered at the origin. There's no shift up or down. All right, the next one says, how do the two functions compare to the parent function? Okay, and again, the smaller the a value, the wider the parabola. Okay, the smaller the a value, the wider the parabola. And that's true up until I hit 0. In fact, if I had the equation y equals 0x squared, you would actually get a horizontal line like this. You no longer have a parabola. And you have no parabola because the x squared term no longer exists. Okay. And so when we say the smaller the a value, the wider the parabola, that's true down to the number 0. And so let's talk about in general, right? So in general, we could say that when given y equals ax squared and that a value is between 0 and 1, okay? So a has to be bigger than 0. If it's 0, I don't have a parabola. But the numbers, the coefficients for these parabolas are smaller than 1, right? 1/2, 1/4, 1/8, etc. Okay. Then the parabola has a vertical compression. Okay, so some keywords here that I want to make sure that we highlight, okay? Again, y equals ax squared. This time a is between 0 and 1. And when that happens, we get something called a vertical compression. And that compression means that we are going to get closer, okay? We are going to push towards the x-axis. We get a flatter graph, okay? And so instead of stretching my arms way up in the air for a vertical stretch, I'm pushing my arms down so that they are more like airplane arms, okay, with this vertical compression. And again, that occurs when I have this a value between 0 and 1. Okay, so now we're going to take all of this new knowledge and we're going to apply all these pieces of opening up and opening down and the properties of the parabola and shift up and shift down and stretches and compressions and apply those all to our quadratic equations.